So today we're going to wrap up Pascal's triangle and combinatorial proof. So basically just going to finish the slides that I wanted to finish on Tuesday. And then the rest of today we'll be walking through problems from homework 6. Okay? But I'm not going to post the work I do when we walk through problems from homework 6, nor am I going to post the webcast. It encourages you to take notes and instead of it rewards people for coming here because it's basically just doing homework 6 for you. Okay? Is that fair? Okay. Quiz 4 is in class on Tuesday from 3:40 to 4:10. So it's just, first 30 minutes, just the same as quiz 1 and 2. It'll cover everything that we've seen since quiz 3 up to and including today. So I highly recommend you work on homework 6 if you haven't already because the questions will be of a similar style to homework 6. Okay. And a couple people asked on Piazza regarding grades in the course. So after this quiz on Tuesday, after you take that and it's graded, I'll tally up the total number of points you have in the course. So factoring in quiz 1, 2, 3, 4 and homeworks through 6, I guess, and determine the number of points that you'll need to earn on quiz 5 and the remaining homeworks to pass the course. Does that sound okay? Cool. So that probably will get done at the end of next week, probably. Okay, any questions logistically with what's going on? And I'll post the solutions to homework 6 immediately after the deadline, just so you have them all day Monday, but we're going to go through a lot of it today as well. Okay, great. So let's pick up where we left off on Tuesday, and we introduced Pascal's triangle, okay? And the first thing that I showed you was that it's really just made up of these terms of the form n choose k. Okay, so the 0th row, and we start counting at row 0. The 0 choose 0. And then, for example, the nth row is all the elements n choose 0 through n choose n. Okay, so the nth row has n plus 1 elements. Okay, and then we looked at some patterns that we can find in Pascal's triangle. Okay, and so this is the slide that we looked at last class. And so the purple diagonals. Well, first let's start with the yellow diagonals. So the yellow diagonals were just the list of natural numbers, right? 1, 2, 3, 4, 5, 6, 7, so on and so forth. It tells you the row number essentially, and remember we're starting counting from row 0. So that's the row number, and these elements are really of the form. These elements are of the form row number choose 1. Okay, and that was the yellow diagonals, and of course Pascal's triangle is symmetric. Then we looked at the purple, or I don't know what color it is, purple or pink diagonal, right? And those elements are of the form row number choose 2, and they form the triangular numbers. Okay, and we saw that if we consider the row number, the triangular numbers essentially correspond to the sum of the first n natural numbers, if that makes sense. Any questions with that? Okay, so for example, here we have 3 choose 2 being 3, 4 choose 2 being 6, 5 choose 2 being 10. So if we want the sum of the first n natural numbers, this was a typo actually. This should be n plus 1 choose 2. Is that clear? Because here we look at the triangle of height 3. That's the sum of 1 plus 2 plus 3 is given by 4 choose 2. Here we look at this triangle of height 4. Then we're looking at 1 plus 2 plus 3 plus 4, and that's given by 5 choose 2. Is that okay? So that's another pattern that's evident in Pascal's triangle. And you can actually work out and show that this is correct, because remember, if you think back to, maybe a month ago, we showed that this formula is equal to n times n plus 1 over 2. But if we evaluate n plus 1 choose 2, well, that's n plus 1 factorial over 2 factorial n minus 1 factorial. But you can work out the arithmetic, because you can write the numerator as n plus 1 times n minus 1 factorial by the recursive definition of the factorial. On the denominator, you have 2 factorial, which is just 2. and n minus 1 factorial, and those cancel. And you're left with the exact same thing that we derived before. Is that clear? So the sum of the first n natural numbers is n plus 1, choose 2. And that's a pattern that you can see in Pascal's triangle. Okay? And the last pattern we looked at was what we informally call the hockey stick theorem. If you make this hockey stick starting from the very left diagonal, or equivalently from the very right diagonal, the number at the very bottom, so the stem of the hockey stick, is equal to the sum of the numbers along the shaft. Okay? So 1 plus 4 plus 10 plus 20 is 35. I can do a similar one over here. For example, 1 plus 6 is 7. 1 plus 4 plus 10 is 15. 1 plus 5 plus 15 is 21. So on and so forth. So that's the hockey stick pattern. So any questions with these patterns that we can see in Pascal's triangle? Okay? And there are more, but I don't want to go over all of them because, I need to have some questions to put on the quiz. So that's that. Okay, so this is essentially what the structure of Pascal's triangle looks like, right? And all of the patterns that we see here highlighted, we can just translate into being some relationship between terms of the form n choose k. Okay, and that's what we're about to do when we start looking at combinatorial proofs. Okay, so essentially the property that defines Pascal's triangle, the one where we have two adjacent elements, when you sum them, it gives you the number below them, that's encapsulated in this identity, n choose k plus, this should be n choose k plus 1, is equal to n plus 1 choose k plus 1. Is that clear? It's saying take a number and the number next to it, add them together, you get the number that's below them. Is that clear? So this is called Pascal's identity, and I believe it appeared on the homework this week, right? Doing an algebraic proof of it. So any questions with where Pascal's identity comes from? It says you take two adjacent elements, and their sum is the number directly below them. Okay? Sounds good? Okay, and another property you might notice just by looking at these numbers on their own, if you add all of the elements in any one row, you get 2 to the row number. So the sum of these elements is 2 to the 0, here 2 to the 1, 2 to the 2, 2 to the 3, so on and so forth. Okay? Not just a coincidence. And so that's sort of the first combinatorial proof that we'll look at. Okay? And so the main idea in a combinatorial proof is instead of proving a statement algebraically, okay, as you may be used to previously, we can prove statements combinatorially by showing that both the left-hand side and right-hand side are both counting the same quantity. Okay? And so a vague way of thinking about this is there's multiple ways to count the number of students that are in this room. Right? I could have a Google form and make you all fill it out. I could sit here and point at each of you and count in my head. But all of them should arrive at the same number because there's only one number of students in this room. Okay, so essentially what this is saying is all the ways that you can count a certain quantity should be equal. Okay, and that's how we will look at combinatorial proofs. We'll show that both the left-hand side of the expression or the equation and the right-hand side of the equation prove the same thing, or count the same thing. Sorry, is that clear? Yeah.
In any cases where your count is not equal.
What do you mean by that?
Like in the sense that, like in a situation where the same solution can have different counts and then they're not going to be equal.
Different ways, the same thing can't have different ways to count it.
For example, you mentioned that both sides are going to have the same number, right? Same count, and that's how we're going to prove that they're equal in a way.
We're going to show that both sides are two different ways of counting the same quantity.
Yeah, same
Okay.
quantity, right? But could it be possible that if you have the same count, then it leads to different quantities? So that you don't have one unique counting it? Are you getting the thing?
Kind of. Well, we're told that this is true, Like, we're told that this statement is true. We just want to prove it.
Oh,
If that
you
makes
only
sense.
assume that it's the case.
Yeah,
Okay.
if that makes sense. Our job is just to give an argument why the left-hand side and right-hand side are both two different ways of counting the same number, if that makes sense. They're two different ways of counting the number of students in this room. Okay? And so the first one we'll look at is a combinatorial proof of the fact that the sum n choose 0 plus n choose 1 plus n choose 2 plus ... through n choose n is equal to 2 to the n, which is a proof that the sum of the nth row of Pascal's triangle is 2 to the n. Do you agree with that? Because these are just the elements in the nth row of Pascal's triangle. Okay? And so let's do an example of a combinatorial proof. Okay? And so what we're going to do is show that both sides count the number of subsets of a set with size n. Okay, so let's just assume we have some set S that's finite and has n elements in it. And what we're going to do is show that both the left-hand side and right-hand side count the number of subsets of the set. Okay? And so on the left-hand side, we know that the subset could either have 0 elements in it, 1 element in it, 2 elements in it, so on and so forth, all the way until n minus 1 elements or n elements. Okay? How many subsets have 0 elements? Well, that's just n choose 0. How many subsets have 1 element? N choose 1. How many have 2 elements? N choose 2, and so on and so forth. Is that clear? Okay? So if we want to look at a concrete example, we could just say S is A, B, and C, for example. And so since the cardinality of S is 3, there are 4 possible sizes of any subset, right? 0, 1, 2, or 3. So the subset of size 0 is the empty set. Of size 1, we could have just A on its own, just B on its own, and just C on its own, right? And how many of those are there? Well, 3 choose 1. And of these, there are 3 choose 0. For 2, it's just all pairs. So the set AB, the set AC, and the set BC, right? And how many of those exist? 3 choose 2. And a subset with 3 elements, well, it's just A, B, and C, the entire set. Okay? Therefore, the total number of subsets of a set with size 3 is 3 choose 0 plus 3 choose 1 plus 3 choose 2 plus 3 choose 3. Is that clear? Cool. Now let's look at the right-hand side. And so this was just an example, but the formal proof just involves an arbitrary value n. Okay, what's at the top is just an example. Okay, then we look at the right-hand side. So another way of counting the number of subsets of a set is, suppose we have n elements. When creating a subset, we have 2 options for each element. Either it's included in our subset or it's not included. Okay, this is similar logic to when we counted the number of factors of a number, right? We prime factored it, and then for each exponent, we said they were whatever. If our number had a factor of 2 to the 4, we said there was 5 options, right? Either we use 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, or 2 to the 4. It's similar logic here. For each element, when we're creating a subset, either it's included in the subset or not. Okay? So for each element in the set, for example, we have S1, S2, Sn, include or don't include. Include or don't include. Okay? And since there's n elements and we're multiplying, we have 2 options for each element. The total number of options we have in creating a subset is 2 to the n. Okay? And so on one hand, we counted the number of subsets as being n choose 0 plus n choose 1 plus ... plus n choose n. And on the other hand, we said that this number should be 2 to the n. And since we're counting the same thing and we had no flaws in our logic, these 2 quantities must be equal. And so that's a completely valid proof that the sum of the sum of the nth row of Pascal's triangle is 2 to the n. So questions with that? So we gave an argument that whatever the left-hand side enumerates and whatever the right-hand side enumerates are really the same thing. In this case, that example was the number of subsets of a set of size n. Okay, and this question is actually also in your homework, number 1. Okay? And so the way to get familiar with doing combinatorial proofs is really just by doing examples. So we'll go through a couple more examples right now. Okay, and you'll have some time to work on some on your own. And so here's another example. We want to prove that m plus n choose 2 is equal to m choose 2 plus n choose 2 plus m times n. Okay? And so the story we'll tell is, suppose we have m Warriors fans and n Lakers fans. Okay? And so what we're going to say, the left-hand side is a number of ways to select 2 basketball fans from the total set of Warriors and Lakers fans. Okay? We have m plus n people. We want to select 2 of them. The total number of ways we can do that is m plus n, choose 2. So the left-hand side is pretty straightforward. Okay? The right-hand side, the way we arrive at that expression, is we look at 3 possible cases. Okay? Either the 2 basketball fans we select are both Warriors fans, and since they're m Warriors fans, the number of ways we can select 2 of them is m choose 2. So that's the first step. Or both of the fans we select are Lakers fans, and since there are n Lakers fans, the number of ways we can select 2 of them is n choose 2. Or the final case where we select 1 Warriors fan and 1 Lakers fan. Okay? How many ways can we select 1 Warriors fan? Well, that's m choose 1. And how many ways can we select 1 Lakers fan? That's n choose 1. So that gives us m times n. And since these are 3 separate cases, they're disjoint cases, right? It's an or in each case, and there's no way you could overlap between any of these cases. We just add them to get the total number of ways we can select 2 of our basketball players. Okay? So the left-hand side, we arrived at this quantity directly. We just said we have m plus n players, or m plus n basketball fans. We want to select 2 of them. Just say m plus n choose 2. On the right-hand side, we broke it up into 3 cases, found out the number of ways we can do it in each case, and added them together. And since both are counting the same quality, they must be equal. Quantity, they should be equal. Is this okay? So this is a lot more straightforward, or I wouldn't say straightforward, but it's a lot less messy than bashing out the arithmetic and showing that it happens to be equal. Okay, in this particular case, it ends up working okay. Like you could say this is, m plus n factorial over 2 times, you could do the math and it would end up simplifying. But for example, if we were to do this case, it would be very, very hard to make the arithmetic simplify, to start with the left-hand side and approach the right-hand side. Okay? And so the beauty of doing combinatorial proofs is that you don't have to work out any algebra. It's just a counting argument. Is that sort of clear? Any questions with this example? Okay? And so now, I'll allow you to work out an example on your own. So let's look at Pascal's identity, which was just the identity that arrives naturally from Pascal's triangle, right? N choose k plus n choose k plus 1 being equal to n plus 1 choose k plus 1. So I want you to think of a combinatorial proof for this. So I'll give you a couple minutes, work with those near you, try and figure this one out. Okay? So any ideas? Can anyone think of a combinatorial proof of Pascal's identity? Any ideas? Any ideas for a combinatorial proof? Sure.
Well, on the right-hand side, it suggests that we're taking like k plus 1 out x 1 and plus 1 total.
Okay. Yeah. So we know on the right-hand side, it's saying we have a group of n plus 1 things. We're choosing k plus 1 of them. Okay. So we want to show that the left-hand side is another way of counting that same thing. Is that clear? Okay. So, and there's an algebraic proof for this, which is actually what's on your homework. I don't know why I'm showing you that. So let's think of this combinatorially. Okay? So again, suppose we have a group of n plus 1 people and we want to select k plus 1 of them. What we can do, and so let's just say our people are p1, p2, ... through pn plus 1. Okay? What we can do is focus in on the very first person. For them, there are two options. Either they're included in our subset or they're not included, right? We're selecting the subset of k plus 1 of our people, and there's two options for the very first person. Either they're included or they're not included. Okay? If the first person is included, there are n remaining people, and we need to select k of them, right? Is that clear? Because we had n plus 1 total, and we had to select k plus 1 of them. But if we're selecting person 1, we only need to select k of the remaining. Because we've already selected our 1. Is that clear? Okay. And then our second case, and of course you can do that in n choose k ways. Our second case is person 1 is not included. Right? And so in that case, there's still n people remaining, but we need to select k plus 1 of them. Because we need k plus 1 people total. In the first case, we selected person 1, so they're now part of our group, so we only need to select k remaining, or like k of the remaining. But in the second case, we're not selecting person 1, so we still need k plus 1 people. Is that clear? And so in that case, you can do this in n choose k plus 1 ways. Is that clear? And so those are our only two cases. Either the first person is included in our subset or not included in our subset. If they're included, there are n choose k ways to select the remaining of the subset. And if they're not chosen, there are n choose k plus 1 ways to select the remainder of our subset. And since those are the only two cases and they're disjoint, they can add them. So we have n choose k plus n choose k plus 1. But we counted the exact same thing, right? The number of ways to select k plus 1 people from a group of n plus 1. Therefore, the left-hand side and right-hand side have to be the same. Is that okay? So for this example, we just focused on the very first person. Either they're included in our subset or they're not included. Thank you. Any questions with this combinatorial? Okay, another example I've seen for this one is, either way it's going to be some justification of how to choose k plus 1 people from n plus 1. But you could look at a bit string of length n plus 1 and say that it has to have k plus 1 zeros or k plus 1 ones. And then you just look at the first bit. Either it's a 1 or a 0. Right? If it's a 1, you only need to select k from the remaining. But if it's a 0, you still need to select k plus 1 from the remaining. Okay? But it's really the same thing. Bit strings, people, it's for this example, it's the same. Is that okay? Great. And so now here's another example I want you to work out on your own. So give a combinatorial proof of Vandermonde's identity. Okay? It says m plus n choose R is the sum of k being equal to 0 up until R, of M choose K, N choose R minus K. Okay, and the hint I'll give you is think of the Warriors-Lakers example of choosing basketball fans from a group of M Warriors fans and N Lakers fans. Okay, so I'll give you a couple minutes. I really want you to discuss this with the people near you, and then we'll come back together and take it up. Yeah. Yes, the summation includes both. The K is not defined outside the summation. Okay. Let's take it up. So this is actually very similar to one of the counting examples we looked at the end of last class. Okay? Remember, we wanted to look at the number of ways, and so the example was, suppose I have 8 boys, 9 girls, I want to select 8 children. Okay? We said the total number of ways to select them is 17 choose 8, but the number of ways I can select at least 4 boys to form the group is I could either choose 4 boys and 5 girls, 4 boys and 4 girls, 5 and 3, 6 and 2, 7 and 1, or 8 and 0. Alternatively, I could start with the total and subtract out the number of ways to select 0 boys, 1 boys, 2 boys, or 3 boys. Right? And we saw that our sum, like this is exactly Vandermon's identity, if that makes sense. Right? The first way we counted the number of ways to choose at least 4 boys, we did it directly, right? We did 8 choose 4, 9 choose 4, so on and so forth. And notice every time the number of boys we chose increased by 1, right? We went from 4 to 5. The number of girls we chose decreased by 1, right? We went from 4 to 3. Because the total number of people we chose has to be constant, right? We're always choosing 8 people in each of these cases. And so that's exactly the same as what we're doing over here. Okay, so we can see the left-hand side is the number of ways to choose R basketball fans from a group of M Warriors fans and N Lakers fans. Okay, I guess here we're assuming R is less than both M and N. Less than or equal to, I guess. Okay? Well, to be more specific, it should be less than or equal to the minimum of M and N, but whatever. Okay. And so now, on the right-hand side, our justification will be, is suppose we want to choose R basketball fans from this group. Whatever number of Warriors fans we choose, the remaining all have to be Lakers fans, right? Suppose R is 10. If we choose 2 Warriors fans, we have to choose 8 Lakers fans. If we choose 3 Warriors fans, we have to choose 7 Lakers fans, right? So whatever R is, if we choose K of our R to be Warriors fans, the remaining R minus K have to be Lakers fans. Is that clear? And so what we do is we add this up over all possible cases, right? Because either we choose, 0 Warriors fans, as it should be, and R Lakers fans, or 1 and R minus 1, 2 R minus 2, so on and so forth. And those are all different cases. There's no overlap in them, so we can just add them, and that gives us our total. Is that okay? Nobody laughed at my joke, I'm sad. It's okay. So any questions with this? We break it up into a bunch of separate cases where we choose K Warriors fans, R minus K Lakers fans, and we sum that up for all possible values of K. Does this sound okay? Cool. Also, a nice little fact that comes from there is if you let M, N, and R be equal, you get that 2N choose N is the sum of the squares of the nth row of Pascal's triangle. Okay, so essentially what that's saying is 2N choose N is really N choose 0 squared plus N choose 1 squared plus ... plus N choose N squared. So it'd be very hard to determine that just using the algebra that you know, but using these combinatorial arguments, it makes it significantly easier to prove things like this.